Welcome everyone. Today, we are launching an investigation into one of the most significant developments in the Australian energy transition. Australia has just approved a 50-megawatt hydrogen plant at the Hunter Valley Hydrogen Hub, located on Kooragang Island. On the surface, this is a major win for renewable energy. But as professional observers, we have to ask the difficult question: will the economics actually work? This project reached its final investment decision on July 1st, 2026, and today we are going to look under the hood to see if this is a repeatable model for the future of industry, or a one-off project kept alive by government support. We will examine the technology, the partners, and the brutal reality of the numbers. To understand why this project matters, we have to understand how the Australian economy actually functions at the ground level. Every single Australian mine, from the iron ore pits of the Pilbara to the coal basins of the Hunter Valley, starts its day with a specific chemical. Before a single ton of rock is moved, something has to break it. That something is ammonium nitrate. This chemical is the essential force behind our mineral exports. But ammonium nitrate doesn't exist in a vacuum. It begins its chemical life as ammonia. The transformation from NH3 to nitric acid and finally to ammonium nitrate is the invisible pulse of our primary industry. Without this chemical cycle, the Australian mining sector simply stops moving. Ammonia is what we call load-bearing infrastructure. It is an invisible molecule that supports almost every aspect of modern life. Yet almost nobody outside of heavy industry ever talks about it. In mining, it provides the explosives that start every extraction. In agriculture, urea and nitrate fertilizers are the reason Australia can produce such massive grain and cane yields. In our food systems, industrial refrigeration for meat and dairy depends on it. Even in water treatment and pharmaceuticals, ammonia is a critical feedstock. Almost everything you touch, eat, or use today depends on a steady supply of ammonia. It is not just a chemical. It is the foundation of our standard of living and the silent partner in our national food and resource security. So, where does all this ammonia go? In Australia, the distribution is very clear. Roughly 60% of our domestic consumption ends up as fertilizer to feed our crops. The remaining 40% is almost entirely dominated by explosives for the mining industry. This demand is concentrated heavily in Western Australia and the eastern coal basins. When we talk about the ammonia market, we aren't talking about niche applications or experimental uses. Agriculture and mining are not side markets for this molecule. They are the market. This means any change to how ammonia is produced or priced will have a direct and immediate impact on the two largest sectors of the Australian economy. The stakes for decarbonizing this specific molecule could not be higher. We are looking at a $1.7 billion domestic market that quite literally cannot be switched off. By 2025, the Australian ammonia market size is expected to hit $1.74 billion US, and it is forecasted to grow at a compound annual growth rate of over 4%, reaching $2.5 billion by 2034. Because 60% of this goes to agrochemicals, we are talking about the price of food. Decarbonizing ammonia is not an optional green gesture or a corporate social responsibility project. It is a fundamental question of survival. Can Australian mining and farming maintain their critical input supply as the world moves away from fossil fuels? If we can't solve the ammonia problem, we can't solve the industrial decarbonization problem. Here is the core problem. Ammonia is currently made from natural gas, and it isn't used for the heat the gas provides. Through a process called steam methane reforming, we strip the hydrogen out of methane molecules. In this process, the gas is not the energy source, it is the raw material. This is why ammonia production is among the most carbon-intensive industrial processes on the planet. You cannot fix this problem by simply plugging the factory into a wind farm. Even if the entire plant was powered by renewable electricity, the process would still require methane as a feedstock to provide the hydrogen atoms. This is the hard-to-abate reality that makes industrial decarbonization so much more complex than just changing a power source. The engineering challenge is simple but brutal. You cannot electrify a feedstock. You have to replace the molecule itself. Today, we take CH4 methane and add water to get hydrogen, but carbon dioxide exits the stack as a byproduct. To change this, we must use an alternative, H2O and electricity. By using electrolysis to split water, we get the hydrogen we need, and only oxygen enters the atmosphere. Carbon never enters the process at all. This sounds perfect on paper, but it requires a total reimagining of the industrial flow. We are moving from a world of extracting energy from fossil fuels to a world of using renewable energy to build the molecules we need from scratch. It is a shift from extraction to synthesis, and the costs are vastly different. This brings us to the location of our investigation, Kooragang Island in Newcastle. This is not a greenfield site on an empty coastal plain. It is a gritty working ammonia plant in the middle of one of the world's busiest ports, right at the mouth of the Hunter Valley coal basin. The facility already has 210 permanent staff and produces 360,000 tons of ammonia every year. It consists of one ammonia plant, 3 nitric acid plants, and 2 ammonium nitrate plants. Crucially, this is a factory that already has a customer base. By choosing a brownfield site, the project team avoided the massive risk of building a new facility from scratch. They are bolting a new technology onto a machine that is already running and already making money. On July 1st, 2026, the project hit a milestone. Orica said yes. This became Australia's largest renewable hydrogen project to reach a final investment decision. The partnership structure is key to its survival. Orica, the owner and operator, is also the off-taker. They are the ones who will use the hydrogen. Plug Power, a NASDAQ-listed company, is supplying 50 megawatts of Geneco PEM electrolyzers, their largest order in the Asia-Pacific region to date. And then there are the underwriters, ReNEnergy and the New South Wales government. Through the Hydrogen Head Start program, they are providing the capital grants and production credits that make the math work. This isn't just a corporate venture. It's a public-private partnership designed to de-risk a technology that the market isn't yet ready to fund alone. But the road wasn't smooth. Originally, ReneEnergy was a major partner in this project. Then, in late 2024, they walked away. The CEO, Frank Calabria, was very clear about why. He stated that the hydrogen market was developing more slowly than anticipated, and the risks regarding input costs and technology were too high to justify a final investment decision. This is the tell in our story. Why could a chemicals company like Orica make this pay when a massive energy company like Origin could not? The difference isn't the technology. The electrolyzers are the same. The difference is the need. Orica needs the molecule to sustain its existing business. Origin was looking for a new market to sell into. For Orica, hydrogen is a survival strategy. For Origin, it was just another investment option that didn't meet the hurdle. Let's talk about the hardware. The project uses 50 megawatts of proton exchange membrane, or PEM, electrolysis. The water source is recycled water, which is a smart move that avoids the need for expensive new desalination plants. The power is grid connected, but backed by LGC and REGO certificates to ensure it qualifies as green. The expected output is approximately 4,700 tons of hydrogen per year. P technology is favored here because it can handle the fluctuations of renewable energy better than older alkaline systems. It can ramp up and down quickly, which is essential when you are trying to balance the cost of grid power with the need for constant industrial output. This is the cutting edge of industrial-scale water splitting. However, when we run the numbers, we see the first major engineering constraint. A 50 megawatt electrolyzer running flat out at 100% utilization should theoretically produce close to 8,000 tons of hydrogen a year. Yet, the project only states an output of 4,700 tons. That is an implied capacity factor of only 60%. Why? Because grid electricity is only worth buying when it is cheap and clean. If the price of electricity spikes, the electrolyzer stack has to sit idle, otherwise the cost of the hydrogen would be astronomical. This is the central tension of green hydrogen. Utilization, not nameplate capacity, is what you actually sell. An idle stack is a capital investment that isn't generating a return, which is a massive drag on the overall project economics. Now look at the second constraint. All of that investment and technology is designed to displace only 7.5% of the plant's total gas demand. The 4,700 tons of hydrogen will produce 26,000 tons of low-carbon ammonia, avoiding 35,000 tons of CO2 per year. To some, 7% sounds like a failure. But in reality, this was a brilliant design decision. By keeping the hydrogen slice small, Orica made the investment survivable. They created a project small enough to finance and small enough to learn from, without betting the entire future of the plant on an unproven technology. It is a controlled experiment at a commercial scale, allowing them to gain operational experience while the rest of the plant continues to run on reliable natural gas. What is Orica actually spending? The construction capital expenditure between 2026 and 2029 is estimated at $245 to $283 million, after accounting for government funding. For Orica, the net capex for the year 2026 alone is between $25 and $37 million. To put that in perspective, Orica's total business capex for 2025 is $460 million. This means the hydrogen project is a significant but manageable part of their overall budget. Construction is slated to start in 2026, with the first green hydrogen targeted for early 2029. This long lead time reflects the complexity of integrating new hydrogen technology into a high-pressure, high-temperature chemical environment like an existing ammonia plant. Now, let's look at the money behind the money, the subsidy stack. The public support for this single 50-megawatt facility is staggering. The ReneEnergy Hydrogen Head Start program is providing $432 million in production credits over 10 years. Add $70 million from the Federal Regional Hydrogen Hubs program and $45 million from the New South Wales government. That is a total public commitment of roughly $547 million. Compare that to Orica's net capex of under $300 million. In simple terms, the government is paying more than half the bill. This shows just how far green hydrogen currently is from being commercially viable on its own. Without this massive injection of taxpayer funds, the project would never have reached a final investment decision. This creates a fascinating contradiction. The subsidy is actually larger than the direct corporate investment. If you spread that $432 million production credit across 10 years of output, the public is effectively contributing about $9 for every single kilogram of hydrogen produced. The target price for green hydrogen to be competitive is around $3 per kilogram. So, the government is paying 3 times the target cost just to bridge the gap. This 10-year credit is a runway. It gives Orica a decade to figure out how to drive costs down before the project has to stand on its own 2 feet. It is a massive bet that by 2039, the technology will have matured enough to survive without the training wheels of government support. Why can't green hydrogen clear the bar yet? There are 2 structural cost floors. First is the electrolyzer capex. In 2026, a Western-made PEM electrolyzer costs between $2,000 and $2,500 per kilowatt. While that is down 25% since 2022, it is still 2 to 3 times more expensive than Chinese alkaline systems. Orica chose the more expensive Western PEM for its reliability and performance. Second is the idle stack penalty. Because the capex is fixed but the output is not. Every hour the stack sits idle waiting for cheap renewable power, the cost per kilogram of the resulting hydrogen climbs higher. Modeling suggests that even with favorable conditions, Australian solar-driven hydrogen won't hit that $3 a kilogram target until at least 2030. We are currently paying a premium for early adoption. While this 50-megawatt project is moving forward, the Australian landscape is littered with the wreckage of much larger dreams. The gigawatt-scale megaprojects are dying. Look at CQH2 in Gladstone, a massive 3-gigawatt proposal that would have cost $14 billion. Stanwell withdrew in 2025 because they couldn't sign any long-term buyers in Japan or Singapore. Gibson Island was abandoned in 2024 because the host plant shut down entirely due to gas prices. Even Fortescue cancelled their Gladstone PM50 project in 2025. None of these projects failed because the physics didn't work. They didn't fail because the engineering was impossible. They failed because they couldn't solve the contract. They had no guaranteed buyers, no existing infrastructure to plug into, and no way to manage the massive capital risk. They were built on ambition rather than foundation. This brings us to the pattern of success. Hydrogen megaprojects do not fail in the plant, they fail in the contract. The megaproject model involves building a new plant on empty land, selling to a buyer who doesn't exist yet, and depending on expensive export shipping infrastructure. It is a multi-billion-dollar bet on a future that hasn't arrived. In contrast, the brownfield model used by Orica is to bolt an electrolyzer onto a running factory. The buyer is the plant next door. They are already consuming hydrogen. By using the existing port, the existing grid, the existing water supply, and a workforce that is already on site, you remove the biggest variables that kill projects. You aren't betting on a new market. You are betting on a known demand line. The single most important fact about this project is this. Orica's customer for this hydrogen is Orica. There is no offtake negotiation. There is no export terminal to build. There is no shipping contract to sign. There is no foreign buyer to convince. The hydrogen is simply piped a few hundred meters into an ammonia plant that already consumes the equivalent in methane every single day. This removes the market risk entirely. The single variable that killed the multi-billion-dollar CQH2 project in Gladstone is the one variable that this project never had to solve. This is the difference between a project that makes headlines and a project that actually gets built. It's all about the off-taker. We also need to consider what Orica did not have to build. A greenfield project would have had to raise billions just for infrastructure before producing a single kilogram of hydrogen. Orica already had the ammonia plant running at 360,000 tons per year. They already had an industrial-scale grid connection. They used recycled water, so no new desalination was needed. They utilized the existing Newcastle port and logistics network. They had a workforce of over 200 people already on site. And they had the downstream nitric acid and ammonium nitrate plants ready to take the product. This project isn't just about an electrolyzer, it's about the massive pre-existing industrial ecosystem that allows that electrolyzer to be useful. Is this project small enough to build, but too small to matter? Let's look at the scale, honestly. 35,000 tons of avoided CO2 will not decarbonize the Australian industry. 10 permanent operational roles will not solve the unemployment challenges of a changing energy landscape. And $75 million in local investment is a drop in the bucket of the national economy. However, as the saying goes, a project that operates is worth more than a project that is only announced. CQH2 promised 100 times the scale but delivered 0. Orica is delivering a working proof of concept. It provides the data and the operational experience that will make the next 500 megawatts possible. It is the necessary first step. The wider implication for Australia is massive. We have dozens of these host sites across the country. Refineries, alumina plants, nitrate producers, steel mills, and cement works. Each one of them is already buying hydrogen or natural gas. Each one is a potential host for a 50 megawatt retrofit. The replicable pattern here is not the technology, it is the conditions. You need an existing plant that already consumes the feedstock. You need grid and water infrastructure already paid for by the host business. You need an operator who is the off-taker, removing market risk. And you need a retrofit slice small enough that failure does not threaten the parent company. If we follow this brownfield model, we can decarbonize industry piece by piece. But let's do one final reality check. There are 4 things that could still break this. First, the subsidy cliff. In 2039, those credits disappear. Can the cost come down enough by then? Second, grid price exposure. Wholesale price volatility flows straight into the cost of every kilogram produced. Third, stack degradation. These PEM electrolyzers lose efficiency over time, and the expensive replacement costs might hit right when the subsidies are ending. Finally, the 7.5% problem. To displace the rest of the gas at this one plant alone, we would need 600 megawatts of electrolysis and a renewable power supply that simply does not exist yet. We are looking at a bridge, but we haven't finished building the other side. This project is a successful start, but the scale of the remaining challenge is immense. The final verdict? The evidence of Orica's success is found in the wreckage of the alternatives. Australia's gigawatt-scale project had more ambition and more political backing, but they all collapsed because they lacked a customer and a host. The Hunter Valley Hydrogen Hub reached its final investment decision because it inherited its customer, its infrastructure, and its workforce on day one. But let's be honest, commercially realistic is not the same as commercially viable. This project only works because of $547 million in public money and because it only touches a tiny fraction of the plant's needs. Integrated brownfield hydrogen is currently the only model in Australia that can be built, but it has not yet proved it can pay for itself. Thank you.